Welcome to lecture number 33 of high performance computing. In the previous lecture, we had started to look at a category of tools called profilers. The use of a profiler is to help us to identify the important parts of our program so that we can concentrate our optimization efforts on just those hopefully small but important parts of our programs. And I had introduced the idea of profilers as automated mechanisms through which the identification of such important parts of our programs can be made. Now, we distinguish between different kinds of profilers in terms of the level at which they operate, which I had referred to last in the previous class as the level of granularity supported by the profiler. And I talked about the possibility of having function level profilers or statement level profilers or basic block level profilers. And a function level profiler would help us to identify the important functions of our program. A basic block level profiler would help us identify the important basic blocks of our program. In addition, profilers might differ in whether they are giving us breakups of execution time or just giving us other pieces of feedback about the performance of our program, such as the number of times that a function was executed or a basic block was executed. And we are going to look at two mechanisms, one at the function level and one at the basic block level. Now, why would function level profiling be a good idea? Now, this question is essentially rephrased as how useful can it be to identify and optimize a few functions of a program. Many of you would have written programs which are extremely large. Typically, the programs that you are interested in optimizing are complicated, otherwise there would be little reason to try to optimize a program. And the more complicated a program is, the larger it is likely to be. And if a program is large and has hundreds of functions, how could it possibly help to just optimize 2 or 3 functions of that program? Now, just to give you some feel for what might not be atypical, what might be a typical property of large programs, I'm going to give you the example of a real world program called the LINPACK benchmark. It's referred to as the benchmark because it is used in doing performance comparisons of pieces of hardware. The idea of a benchmark program is that one runs the benchmark program on a piece of hardware, measures how much time the program takes, and then if you run the same program on another piece of hardware and it takes less time, you will know that the second piece of hardware is faster or better. And one could use analysis based on the performance of benchmark programs in making decisions about what computer to buy, etc. So the whole idea of benchmarking is interesting. But the LINPACK benchmark is one example of a benchmark. And LINPACK itself is acronym for the name of a linear algebra package. What we mean by linear algebra package is a package that does a library of functions for computation on vectors and matrices, multidimensional matrices. Now, the LINPACK benchmark itself uses the LINPACK library to solve a large system of linear equations using Gaussian elimination. So it uses many of the functions inside the linear algebra package to solve a particular problem, which is what I'm referring to you, solving a large system of equations, linear equations. Now, the LINPACK benchmark is a fairly large program in terms of, if you look at the size of the program as well as the size of the libraries, it's a fairly large, it includes many functions. And the execution time of the LINPACK benchmark is fairly substantial. So it is in fact a commercial type of a program in that it is used to make by some people even in making purchase decisions or comparing the performance of large computer systems. Now, as it happens, if one analyzes the LINPACK benchmark in terms of its function level profile, strangely enough, one would find that a significant percentage of the execution time of the LINPACK benchmark is spent in one function. In fact, about 70%, if I remember right, of the execution time of the LINPACK benchmark is spent in a function called SAXP. And we have come across the name SAXP before. We learned about its sibling DAXP. You remember that DAXP was double precision AX plus Y. AX plus Y. Right? We saw this not too long ago. And SAXP is a single precision version of AX plus Y. It's multiplying a vector x, multiplying a vector A. Notice, it's multiplying the vector x by a scalar A and adding this to the vector y and making this the new value of the vector y. A simple operation which we represented by a very small for loop in the case of our C example, not in a few lectures back. 70% of the execution time of this real world benchmark is spent in one function, and the size of this function is just 1 or 2 lines. So very clearly this motivates the idea of function level profiling. It may be the case that by just concentrating on a small number, 1, 2, 3, maybe 4 functions, you may be addressing a large percentage of the execution time of the program that you are trying to optimize. So function level profiling may not be a bad idea. Okay, now the function level profiling mechanism that we are going to talk about is known as Prof, P-R-O-F, Prof standing for profiler, and it is the UNIX function level profiling mechanism. The way that you use Prof, and again I am showing you the interaction in terms of the shell, interaction with the shell, starts, these comments obviously not part of the shell, I have just added them for explanation of what is happening. So you start, if you wanted to use the Prof profiling mechanism, then you must compile your program using the -p option. So GCC or CC -p program.c, and what this does is it causes a special version of the executable to be created. So rather than just compiling your program.c to generate an a.out file, GCC will now compile your program.c to include within the program, the a.out, instrumentation. In other words, instructions through which, when the program is executed, profile data is gathered, and subsequently if you run a program called Prof, you can see the profile data in a human readable form. So it is a 3-step process. You start by asking GCC to compile your program so that it is an instrumented executable a.out, not the ordinary a.out. Subsequently, when you run that a.out, a file full of profile data gets written out, and you can subsequently use another program to look at the contents of that profile data in human readable form on the screen. Okay, what is the output that you see when you run Prof? The output that you get is, function by function, a breakup of the execution time, the percentage of execution time that was spent in that particular function. In addition, it also gives you the number of times that each function was executed. And these two pieces of information will be useful in identifying which functions you should concentrate your optimization efforts on. For example, if you had done this on the LinPack benchmark, you might find out that 70% of the execution time was spent in SAXP, which was called a huge number of times. Now, first question, how does Prof work? How does this entire mechanism work? Now, it turns out that the instrumentation which is included within the a.out file that will be executed when you run the program, the instrumentation does 3 things. One thing that it does is, at the entry of each function, in other words at the beginning of each function in your program, it includes an execution count incrementing instruction. Therefore, what the instrumentation does is it maintains a count of the number of times each function is entered. How does it do this? It actually has a set of counters, one for each function, and at the beginning of each function, when the function is entered, it increments the count for that particular function. Then when the program terminates, it prints out all these counters into the mon.out file. So one piece of instrumentation that is done is that at the entry of each function, a counter for that function is incremented so that the number of times that function was executed can be kept track of. Now another thing that the instrumentation does is that at the entry point of the program, in other words in the early parts of the program, it makes a call to the system call called profile, P-R-O-F-I-L. And what profile is going to do is to get estimates of the execution times within each function. Therefore, the instrumentation itself does not do anything with timing mechanisms. All that the instrumentation does is to call this system call, which is known as profile. Finally, the third thing that the instrumentation does is that at the exit point of the program, in other words just before the program terminates, at that part of the program, it causes the contents of the various counters that have been accumulated to be written into the output file, which we understand has a default name of mon.out. So that subsequently the output file, when the program is run, the output file will contain the information that can be used to understand what happened when the program ran. So the instrumentation does these 3 things. It's very simple. Incrementing a counter at the beginning of each function, calling profile at the beginning of the program, and dumping the various counters of information that have been maintained at the exit point of the program. So instructions to do these things are included by GCC into the a.out. That's what we mean by instrumentation. So now we have reduced our problem to trying to understand what does the profile system call do. If you look at the profile system call details, you will find out that profile is described as an execution time profiler. So it is included as a system call for exactly this purpose, to provide profiles, function level profiles of execution time. And essentially what it does is it generates a histogram of the execution time spent in each function. What I mean by histogram is, for each function, there may be function 1, function 2, function 3. The histogram is the details of how much time was spent in that particular function. So this could be 10 seconds, this could be 8 seconds, this could be 12 seconds, and so on. So essentially that's what profile does. It generates a histogram for each function, how much time was spent in that particular function as far as the execution time of the program is concerned. Let's just see in more detail how profile does this. Now I am referring to profile. Remember that this is the name of the system call which is used by the Prof mechanism. Okay, now to understand this quickly, profile is a system call. It has many parameters. One of the parameters in a call to profile is a buffer or an array. And this array is used as an array of counters, each counter being initialized to 0. Now the different counters inside this buffer array are each associated with some contiguous region of the program text. You'll remember that when we refer to the text of a program, we are referring to the code or the instructions of the program. So what does this mean? This means that the profile has a buffer, an array of counters. The counters are all initialized to 0, and each of the counters is associated with some region of the program, of the instructions of the program. Now during program execution, when the program is actually executing, every once in a while the program counter value is sampled. Remember that PC was the name of one of the special purpose registers inside the CPU. At any given point in time, that particular register contains the address of the instruction which is currently being executed. Therefore, and what I mean by sampled is that every once in a while the system looks at the current value inside the program counter value, inside the program counter register. In other words, what it means to sample the program counter every once in a while is that every once in a while, due to the profile system call, it keeps track of which instruction is currently being executed. And this is done with some period. As I said, it's done every once in a while. In many systems, this is done once every 10 milliseconds. And this activity would actually be triggered by that hardware timer interrupt. You'll remember that within one of the pieces of hardware in any computer system is a piece of hardware that periodically generates an interrupt, and this is critical to the functioning of the operating system, for example in making decisions about doing context switches and so on. So one other piece of functionality that would be included in the hardware timer interrupt handler we now see is going to be related to profiling. Possibly the sampling of the program counter would be initiated out of the hardware timer interrupt handler if that is so required by the program. What then happens is, depending on what program counter value has been identified as the current program counter value, the corresponding buffer element counter is incremented. So if we had found out that a particular load word instruction which has address hex A000 is the one that is currently being executed, then the particular counter in the buffer relating to that particular instruction address would be incremented. And this is how the profile system call gets an idea about the different instructions or the amount of execution time that is spent in each part of the program. Okay, now let's just look at this a little bit more carefully. So what profile does is, I'm just recreating what happened, what was described in the previous slide. So let's suppose this is our program text. This is the different instructions of which my program is made up, what I'm showing on the screen. And I know that the program contains many functions, so I'm assuming that I have functions called main, func1, func2 up to func8. So this particular program we're saying has 9 functions, and I know exactly where each program begins and ends, right? Because I know the compiler compiles main. I wrote the main function, and the compiler compiles the main function into many instructions, and then the compiler compiles the func1 function into many instructions and so on. So when I look at the program text, I can actually view the program text as the different functions. And here I've drawn each of the 9 functions and shaded them in a different color. Okay, now You should also bear in mind that in looking at the program text, I could also view each of the functions in terms of its start address and its end address, because we know exactly how many, we can count how many instructions there are as part of each function, and then we can associate the start address and the end address of each function. Okay, now at the other side, Profile is using, as I mentioned, a buffer, that is an array of counters, and there are going to be some number of counters in that buffer. The number of counters in the buffer need not be the same as the number of functions in the program. It need not be the same as the number of instructions in the program. It just has some number of counters within the buffer. Now, once every 10 milliseconds, remember, the program counter is sampled. So let's suppose that in one particular sample, one particular sample, now the thing to bear in mind is the size of the buffer. Once every 10 milliseconds, a particular program counter value is obtained, and let's suppose that it's some particular program counter value. Now, the size of this buffer is going to be decided based on the system call. It's going to be some size. I'll just refer to it as buff size. So it has elements, counters going from counter 0 up to counter buff size -1. Now, whenever a PC value is sampled, that PC value can be scaled to a value between 0 and buff size -1, depending on what the value is. For example, if the value is 0, we might scale it to 0. If the value is the largest possible value, we might scale it to the largest possible buffer size value. If it's halfway in between, we might scale it to the halfway in between buff counter value. So some scaling is done of the PC value to a value between 0 and buff size -1. And let's suppose this is the value that is currently corresponding to that PC value. Then that buffer counter is incremented. So that's how the PC sampling mechanism happens. So as slowly as the program executes, thanks to the profile system call, once every 10 milliseconds, one or the other of these counters gets incremented. Now, how do we relate this to the execution time of the functions in the program? There doesn't seem to be any relationship between the buffer elements or the counters inside this buffer and the functions of the program. However, we can associate a range of buffers, a range of counters with each of the functions in the program, possibly based on the number of instructions in that particular function. So for example, if main is 20% of the instructions in the program, then I know that the first 20% of the buffer counters are going to be associated with main. And therefore, there is this relationship that we can make between the counters back to the functions. And therefore, while all that the prof output has to tell us or has to be manipulated to do is, all of the counters which relate to the region of program text that were mapped into by the scaling function relating to a particular function can be added together to give an estimate of the amount of time that was spent in that particular function. How much time should be associated with each of the counts? You'll remember that we were doing a sample once every 10 milliseconds, and therefore if the total of all the counts within the region associated with main was 5, then that could be associated to have a value of 50 milliseconds. And similar calculations could be done for all of the functions. This is essentially what's happening behind the scenes as far as the profile system call is concerned. Ultimately, the output would look something like this. Over here, I'm showing you the output generated by running Prof on a matrix multiplication program. Now, in this particular program, I actually had a main function. There was a function to read the matrices in. There was another function to print the result out. There was a function to do the multiplication of the matrices. Within the function to print the matrices out, there was a call to printf, which is a function to do printing. Within the function to do the multiplication, there was a smaller function which was called, which does a step of the multiplication. And then the additional functions which you see over here are actually functions which are called out of printf or out of the other functions in the program. They are actually not functions which are written by me when I wrote the program, but are functions which were added due to the fact that they were possibly part of the libraries that my program called. Now, if I look at the output of Prof, I notice that there's one entry for each function, and I'm told exactly how many times that function was called. I'm also given an estimate of the percentage of time of the total execution time of this program that was spent within the function. So for example, I'm told that 91% of the execution time was spent in the write system call, was spent in a function called write. and I'm also given some information about the number of seconds that that percentage was amounted to. Now you may be wondering, how come this exercise seems to be telling us nothing useful, in that 90% of the execution time was spent in a function that is part of the library and that I had no control over. Now in this particular case, the size of the problem was fairly small. I was multiplying a relatively small matrix, so that the execution time of the program was dominated by the activity of writing the result out on the screen. And that's a slightly artificial situation, in that it would have been more beneficial to me if I was interested in optimizing the program to actually leave out all the functions which have to do with inessentials, such as printing the output onto the screen. When I'm trying to optimize the program, I want to optimize the parts of the program that do the calculation, and therefore it would probably have been a better idea for me to have done the profile run on a version of the program which does not do the output at all. As we clearly see, the output was dominated, the profile output was dominated by the input and output functionalities of this program. Right, so do we have any other guidelines that could be used in deciding how to use Prof? One very clearly was, don't just use Prof in the production. If your objective is to use Prof in order to find out which functions you should spend your optimization efforts on, then certainly don't include all the calls to input or particularly output types of functionalities in your program unless they are essential for the functionality of the program. Okay, so what else can we learn about how to use Prof from our understanding of how it works? Now, a few things that we can understand. First of all, is that Prof operates by using profile, the system called profile, and what the system called profile does is that it causes the PC value, the program counter value, to be sampled once every 10 milliseconds, and subsequently whichever function happens to be executing at that point in time will be given a weightage of 10 milliseconds. The net effect is that the granularity of this profiling mechanism can at best be viewed as being 10 milliseconds. It's not capable of giving me a finer picture of how the execution time is being divided across the different functions of the program. Another thing which I would note from the description of how Prof works is that the profile that is generated could differ for multiple runs of a program, even if I'm running the program on the same data in each of those runs. And the question you'll ask is, how could this happen? Now, the suggestion is that I could run a.out, and then I could run a.out again, and I could run a.out again, and each time that I did this I could get a different profile. And the question is, how could this happen? And the answer, that as you can realize it, is at the time that you do these profiling experiments, there could be other programs running on the system, and the other programs will be sharing the different resources of the computer system with your program, which is currently going through the profile run. Therefore, the behavior of the other program could affect things that affect your program, such as the contents of the virtual memory, the contents of the physical memory, the contents of the caches. And therefore, your program might see different numbers of page faults or different number of cache misses due to the fact that there are other programs running on the system. And therefore, each time that you do the profiling experiment, you could well get different results. So this is something that we have to bear in mind from our understanding of how the Prof mechanism works. Lastly, even though we haven't gone into this as yet, I'll go into this shortly, the output that you get from Prof could actually be completely wrong. And this is largely going to be an artifact of the fact that it samples the program counter once every 10 milliseconds. And this is scary, so we do need to understand how this could happen, and if so, what we could do about it. All right, now the general idea is that in the worst case, every time that the program counter is sampled, it could be that there is a particular function that just happens to be running at that point in time. And let me just illustrate how this could happen. Now, this is an example of how Prof could give really bad time estimates, or a really bad, inaccurate profile of the breakup of execution time across functions. Okay, now you'll remember that we're talking about the real timeline, because we're talking about something that happens triggered by once every 10 milliseconds by a hardware timer interrupt. Therefore, the 10 milliseconds that we talked about was not virtual time of process P1 or virtual time of process P2, but was along the real timeline, the elapsed timeline. It's once every 10 milliseconds. Therefore, once every 10 milliseconds, the virtual timeline, I'm sorry, the elapsed timeline, this is real time or elapsed time, has to be viewed as being broken up into these chunks of size 10 milliseconds. And let me assume for the moment that there is only one program in execution. Forget about the interference from other processes. So it could happen that the first, my program starts executing. It starts by executing a function, and I'm designating that function by the brown time on the real timeline. So that could be the function which is function A of my program. So function A runs for a few milliseconds or less, and then it calls function B, which is the green function, and then function B calls function A again, and then after a little while of execution, function A calls function B, and so on. So you can see that what's happening is that every time the 10 millisecond timer interrupt happens, it just happens that function A happens to be running. But the bulk of the time in between, it turns out that function B is running. Therefore, realistically, if you look at this diagram, you might say function B is running for about 70% of the time, and function A is running for about, or maybe even 80% of the time, and function A is running for about 20% of the time. And therefore, if I had to optimize one of these functions, I would try to optimize function B. But what is the output from Prof going to be as far as this particular program is concerned? Unfortunately, every time the timer interrupt happens, function A is running, and therefore the estimate the Prof is going to give you is that 100% of the time is spent in function A and 0% of the time is spent in function B. So the Prof profile will show 100% of the execution time being spent in function A. And this could happen. It may not be a frequently occurring situation, but it's something that could happen. In other words, Prof could be completely wrong. And we have to somehow take this into account, otherwise we could be in deep trouble. Therefore, we must have some kind of guidelines for using Prof based on our understanding of what is happening behind the scenes when Prof is used. And here are some possible usage guidelines. Okay, now the first usage guideline which people very often make is that you need to make sure that you do the profile run under as light load conditions as you can. And what do we mean by light load conditions? We are talking here about the number of programs running on the system. People often refer to the load on a system by the term system load, and you could quantify the load on a computer system by the number of programs or the number of processes that are currently active on that computer system. So to talk about light load conditions means that we are talking about conditions where the number of processes, the number of programs currently running on that computer system is minimal or is as low as possible. What is the reason for using this as a Prof usage guideline? We saw that if there are many programs running on a system, then I have the problem that if I run my program a.out, then it will suffer from the cache misses, page faults, which are artificially created because the other programs are sharing the resources on the computer system. Therefore, if I wanted to find out the true properties of my program, I would actually want to study my program under conditions where there are few interactions or few nuisances created by the other programs in execution on the system. And that's why the recommendation is to use profile run under light load conditions. Now, even if you do a profile run under light load conditions, there's a possibility that when you run it 2 or 3 times, you get different results. In one, you may be told that 20% of the execution time is in program A. In the other, you may be told that 30% of the execution time is in function A. Therefore, generally it makes sense not just to do the profiling run once, but run it a few times and see if the results vary substantially. For example, if we actually had a situation like what we see over here, but then we ran the profile run 2 or 3 times, then there's every chance to believe that for some of the runs, this exact skewing, this exact match between the time that the timer interrupt occurs and A happen to be executing may not be the case. So if I did 10 profile runs, I might find out that 3 of them give me the wrong profile and the remaining 7 give me something else, maybe closer to the accurate profile. Therefore, to overcome the problem with being completely wrong, it might make sense to do the profiling run a few times, and if the results vary quite a lot, then do it a few more times, and then assume that the majority output from the many runs that you did is the one that is likely to be more typical of the behavior of your program. Okay, now another piece of information that should be borne in mind is, remember that Prof, in addition to giving you this estimate of the percentage or the amount of time that was spent in each function, also gives you the number of times that each function was executed. And that count of the number of times that each function was executed was generated by incrementing a counter that was incremented within the early parts of the function, and therefore the count of the number of times that each function was executed is exact. The timing estimates are the breakup of execution time are only estimates, and they could be bad estimates, but the count of the number of times each function was executed will be exact, and therefore one can always use the execution counts and understand that they are precise, and that there is no reason to think that they could be wrong in any way. Okay, now with this we have an idea about one level of profiling at the function level and we see that there are certain problems with using the function level, but with appropriate guidelines we should be able to get useful information out of using a mechanism like Prof. Now you may be wondering about that 10 millisecond interval of sampling the program counter. On a scale where we have processors that are faster than 1 gigahertz, you will note that in 10 milliseconds there will be a huge number of instructions that could be executed. If we have a processor which is at 1 gigahertz, then every nanosecond it might be executing a single instruction, and therefore in 10 milliseconds you can see that there are millions and millions and instructions that get executed. Therefore, is sampling the program counter once every 10 milliseconds adequate? Shouldn't they be sampling it more frequently? Now you will see that there are some processors, some systems in which they sample the program counter once every millisecond, but that's pretty much the farthest that you may find. It turns out that it is adequate for the purpose that we are talking about to sample the program counter relatively infrequently, because for a long running program you will get a large number of samples, and statistically the number of samples, as long as the number of samples that one gets is adequate to give us an idea of the distribution of time across the different functions, then the number of samples, the interval between two samples is not that important a consideration. Therefore, there is not too much of a concern about the fact that the sampling happens at 10 milliseconds or at best 1 milliseconds. Okay, now with this let's move on to the second profiling mechanism that I said I would talk about, and this is an example of a profiling mechanism which happens at the basic block level, and I'm using one of the early names, one of the early tools which used basic block level profiling, which appeared sometime in the 1980s and was known as Pixie. So this is going to be, as you can clearly imagine, a completely different style of profiling from what was happening in the case of Prof. And I'll suggest a mechanism which could be used for its usage. This is the usage mechanism from the original Pixie tool. So the idea here is that once again you compile your program, but without any particular request to the compiler to do any instrumentation. So this will cause an a.out file to be executed, to be generated. Subsequently, you use a program which does the instrumentation for you. This was the mechanism that was done at the time of Pixie. So a program called Pixie which would take in the a.out and generate an instrumented executable which it called a.out.pixie. So the instrumentation would be done not by the compiler but by another program. Subsequently, you would run the instrumented version of the program a.out.pixie, and this would generate an output file which you could examine using a program like Prof. Right now, unlike the function level profiling, here the output is going to be based on properties of at the basic block level, and there is going to be no attempt to estimate the amount of time spent in executing a basic block, but rather what the Pixie mechanism gave you was execution counts for the different basic blocks of the program. So it is basically an execution counting mechanism, a counting mechanism, not a time estimation mechanism. And this is actually was useful for all kinds of different purposes. In addition to identifying the important parts of programs, it was also used by computer architects for various kinds of architectural studies of programs. Okay, now I've given you in the previous class an idea about what a basic block is. I defined it as a sequence of contiguous instructions in a program such that the only entry into that sequence of the instructions is the first instruction in the program, the first instruction in the basic block, and the only exit from the basic block is the last instruction in the basic block. So in general, one could infer from this that any one of these three could be viewed as being interpretations of what a basic block is. In the first, I describe a basic block as a section of a program that does not cross any conditional branch, loop boundaries, or other transfers of control. And you can sort of see that this is in sync with the first explanation of what a basic block was, because if there is a basic block of which the only entry point is the first instruction and the only exit point is the last instruction, and there are only instructions in between, then quite definitely there cannot be any branch into the middle of the basic block, which means that it cannot cross any conditional branches, etc. So one could argue that this is consistent with our first explanation. Similarly, it could be described as a sequence of instructions with a single entry point, single exit point, and no internal branches. So this no internal branches is an additional observation. You notice that from our first explanation I had said that you could only enter a basic block from the first instruction and you could only leave by the last instruction. But if there was a branch within the basic block, then you could have left from within the basic block, and therefore there can clearly be no internal branches. So this is also consistent with our previous explanation. And finally, this relationship between our first explanation of the basic block and our current two explanations of the basic block, you notice that the current two explanations of the basic block are describing basic blocks in terms of control transfer instructions, branches, conditional branches, loop boundaries, and so on. And therefore one could actually sort of infer that a basic block has something to do with control transfer instructions, and one could view it as a sequence of program statements or instructions that contains no labels and no branches, no control transfer instructions. That's what I mean by branches. Right? And what does it mean to be a label? A label is the target of a control transfer instruction. So this is a somewhat more functional description of what a basic block is. It is some sequence of instructions in a program which have the property that you cannot branch into. In other words, there is no instruction in this sequence which has a label, and further, no instruction in this sequence is a control transfer instruction. And from this it follows that you could only have entered from the top and you could only leave from the bottom, which was our starting definition. So this gives us a functional mechanism through which we can identify basic blocks in programs, and it's a better way to look at programs if one wants to understand basic blocks. Okay, now let me explain how Pixie works in terms of the instrumentation that it does. Now very clearly, you'll remember that under the Pixie framework, Pixie is the name of the program that takes in an executable file and adds instrumentation into that program in order to count the number of times that each basic block of the program is executed. So very clearly, one thing that Pixie has to do is identify the basic blocks of a program, and the other thing that it has to do is it has to add instrumentation into the program in order to count the number of times that each basic block is executed. So the first question in understanding how Pixie works is how can basic blocks be identified? And we're going to look into this a little bit, but it turns out that Pixie used certain heuristics where necessary. What I mean by a heuristic is some kind of a guideline not based on any exact scientific principle, but just a guideline. So let's try to understand how to identify the basic blocks of a program. Okay, now we understood that the basic blocks of a program are defined by the control transfer instructions and the targets of control transfer instructions. Therefore, we could infer that if I could identify all the control transfer instructions in a program, and I could also identify all the target addresses of the control transfer instructions in a program, then I would know the basic blocks of the program. And this gives me the functional mechanism to identify the basic blocks of a program. So let's suppose that I have program text. So these are the instructions of the program from the first instruction going till the last instruction. And I know that I can identify the control transfer instructions because if I examine each instruction of the program and I know the instruction format, then I can decode each of the I can write a program which could decode the instruction and determine if it is a control transfer instruction or not. So it should be possible to identify the control transfer instructions. So if I identify the control transfer instructions, I could mark them. So here I have in red, I have arrows which are pointing away from each of the control transfer instructions in the program. So we've done the first, I've identified the control transfer instructions. Next, I need to identify all the targets of control transfer instructions. In other words, the different places to which a control transfer instruction might transfer control. And once again, if I have each of the control transfer instructions, I could look at the control transfer instruction to identify its target. And I could mark those in the program. So in the green arrows that I have put show you the targets of the different control transfer instructions. And therefore, to identify the basic blocks, all that I have to do is I could say the region in the program between any two of these arrows is a basic block. And that's what I could do. I could mark the regions between these targets of control transfer instructions and the control transfer instructions themselves and say those are the basic blocks of the program. That sounds easy enough. There is of course one problem, and that is it may not be possible for me to actually identify all the targets of the control transfer instructions. Let's just look at a simple example from our MIPS1 experience. Here is a control transfer instruction of the MIPS1, jump register R8. So this transfers control to the instruction whose address is inside register R8. Now as this program executes, it's possible that different values get into register R8. And unless I know all the different values that could get into register R8, I could not possibly know the different targets of this control transfer instruction. And therefore, there are certain problem cases, even for the simple MIPS1 instruction set, which make it practically impossible for us to actually identify all of the targets of control transfer instructions. Identifying all of the control transfer instructions is not a problem because we know the instruction set. But this is why Pixie had to use certain heuristics, but you could sort of understand that for the different possible C constructs which may result in control transfer instructions, such as while loops, repeat loops, switch statements, etc., it might be possible for heuristics to be identified in the event that this kind of an instruction has to be used in the compilation of that particular C construct. And that is why heuristics may have been necessary in the case of Pixie. Okay, so this was the problem with the jump register instruction. Right, so we understand how the identification of the basic blocks could be done. The next question is, what instrumentation would Pixie do? In other words, what would it have to do to generate the instrumented version of A.out? And basically remember that all that Pixie does is it gives us basic block counts, the number of times that each basic block is executed. Therefore, all that has to be done is increment a counter associated with each basic block. So at the beginning of each basic block, include instructions to increment a counter for that basic block, initialize all the counters to 0 prior to that, and at the end of program execution, cause all the counters to be printed into the output file. Right? So on program entry and exit, initialize the data structures and write the profile output file. So the instrumentation seems to be relatively simple. Now at this point we need to ask one question, and that relates to what I'll call the intrusiveness of such profiling mechanisms. We have seen two profiling mechanisms. One was the function level profiling mechanism Prof, the other was the basic block level profiling mechanism which I refer to by the name Pixie. And I raise the question of how intrusive are these, and the underlying issue which we are trying to address is, does the instrumented program behave enough like the original program? Now just remember that in both cases, both the case of Prof and the case of basic block level profiling using Pixie, we did not use the A.out file corresponding to the program that we were interested in. In both cases, we ran an instrumented version of our program, and the instrumented version was not exactly the same as our program by definition, because it contained instructions which were doing the instrumentation or the measurement of the breakup of time or the measurement of the number of times that the basic block was executed. Therefore, by definition, the program that we ran in the profiling run was different from the program that we are interested in, and that therefore if they are sufficiently different, then they may not behave alike, and that one has to worry a little bit about whether the difference between the two programs is so substantial that the intrusiveness has become a problem. Hence the issue is one of relevance. We have to satisfy ourselves that neither of these mechanisms is too intrusive, because if it is too intrusive, then the profile generated might mislead the direction of our program optimization efforts, and therefore it would be counterproductive for us to use the profiling mechanism. Okay, so we need to address the question of how intrusive are these mechanisms. Let me start by talking about Pixie. Okay, now one thing we should note about Pixie is that the instrumented executable program could be much larger than the original program. Is this a problem? Now you should note that if the instrumented program is much larger than the original program, then it could suffer many more page faults, it could suffer many more cache misses, and therefore it could end up having different timing properties than the original version of the program, and therefore this could be a concern. But let's first of all satisfy ourselves that this is a problem with Pixie. Is it the case that the instrumented executable program could be much larger than the original program? Okay, now thinking back to what Pixie did, we understand that it instruments each basic block by adding instructions to increment an execution counter for that basic block. That's all that it did as far as each basic block was concerned. So we have to understand how many instructions it would have had to add into each basic block in order to do this activity. How many instructions would be required to increment a basic block, a counter for that basic block? Now the first thing to note is that these counters cannot be maintained in registers, because the number of basic blocks in a program could be fairly large, and therefore the counters must be maintained similar to the way Profile does it, using memory. And therefore in order to increment a counter for a basic block, there would have to be at least 3 MIPS1 instructions. One to load the counter into a register, one to increment that register, and another to store the value of the incremented counter into the memory location. Therefore, we will suspect that for something like the MIPS instruction set, the instrumentation would amount to 3 instructions for each basic block. Okay, now the next question is that too much? Is that a lot? Now that's going to depend on the size of the basic block. If the size of each basic block is 50 instructions, then adding 3 instructions may not be that much of a problem. But the size, if the size of each basic block is 3 instructions, then adding 3 more instructions to it is going to double the size of the basic block, and that would be a bit of a problem, or that could be a bit of a problem. Therefore, to understand if instrumentation which requires 3 instructions to be added to each basic block is too much, we have to know a little bit more about how big each basic block is. So what is the size of a typical basic block? And this will of course vary from program to program, but we could get some rough idea about how big each basic block is if we had some idea about how frequently control transfer instructions are executed. For example, if we knew that, let's say 20% of all the instructions executed by a program, typical programs, are control transfer instructions, and this kind of an information might be available in different sources of information. Let's suppose that this is the case, then how could we from this get some idea about the average size of a basic block? If 20% of all the instructions executed are control transfer instructions, that means that 1 in 5 instructions which are executed are control transfer instructions, from which we could infer that the size of average size of a basic block is something about 5 instructions, 5, 6 instructions. And if this is the case, in other words, if around 20% of all instructions executed are control transfer instructions, then we could actually infer that adding 3 instructions into a basic block is going to increase the size of the average basic block by about 50%. And that might be a concern. We are increasing the average size of a basic block from about 5 to about 8. And therefore, the size of the program is going to go up by about 50%. All right, now the question of how do we assess whether this intrusiveness is bad and makes Pixie a mechanism that we should be suspicious about. But bear in mind that all Pixie is doing is giving us basic block execution counts. And the accuracy of the count is not going to be affected by the size of the program. Even if the program becomes hundreds of times larger and suffers huge amounts of cache misses and page faults, the accuracy of the count is not going to be affected. And therefore, we don't have to worry about Pixie as far as the accuracy of the counts is concerned. It does not matter because the basic block execution counts are accurate. Okay, so Pixie instrumentation will increase the size of the program, possibly substantially, but we don't have to worry about it because this does not affect the accuracy of the counts. Now what about Prof? Prof is a little different in that Prof is trying to give us accurate, not just accurate execution counts, but also a breakup of execution time. Now in the case of Prof, if you think back to what we discussed, the size of the instrumentation is not very large. What was the instrumentation in the case of Prof? What it did was, at the beginning of each function, it added instructions to increment a counter for the function. So 3 instructions, MIPS1 instructions, would be added to each function. And we understand that the average size of a function is going to be substantially more than the average size of a basic block, and therefore adding 3 instructions into each function should not be viewed as being large. Other than this, all that the instrumentation for Prof did was to include a call to the system call profile, and then at the exit point of the programs to cause the counters which had been accumulated to be written to the output file mod.out. So in the case of Prof, we don't have any reason for concern because the instrumentation is not very large in size, and it's not going to change the properties of the program much for that reason. So with this, we have seen these 2 mechanisms which are available on, mechanisms of these kinds are available on most of the computer systems that you will encounter. Prof by the very same name, variants on Prof such as something called gprof, which will give you another level of information about the relationship between the functions that are called. And in addition to this, the Pixie type basic block level mechanisms, some of which are available directly from instrumentation done by the compiler. Okay, now are there any other mechanisms that we should be aware about that are widely available on computer systems that might be useful to us in getting ideas about the important parts of our programs? So are there other important profiling tools? I would like to mention just one. There are several, but I'd like to mention one, and that is the Intel vTune Performance Analyzer. So this is a product available from available from Intel, and this is available both on Windows as well as for Linux, Linux systems. And basically, this is special in that unlike the previous 2 mechanisms that I had talked about, in other words Prof and basic block level profiling using something like Pixie, vTune provides a way to access something called hardware performance counters. Now, hardware performance counters, as the name suggests, are mechanisms that are available in the hardware for us to get some count information about different performance aspects of what's happening in the hardware when our program executes. And from this we should understand that in addition to hardware counting mechanisms like the timestamp counter, which we saw a little while back when we were talking about timing, modern processors actually contain a variety of other hardware events that can be counted during program execution. And examples of the kinds of hardware events that modern processors allow us to keep track of are things like the number of instructions that have been executed, the number of L1 cache misses that have occurred, or even other kinds of information which we are not entirely aware of. But you can well imagine that if you are able to get information about something like this, the number of L1 cache misses that occurred when your program was executing, then this would be of great value to us in understanding the cache behavior of our program even better, which is why a mechanism like Intel vTune's performance analyzer, which provides access to information not only about cycle counts, but also to other kinds of events such as cache misses, would have additional value to a programmer in understanding what are the important parts of the program and in analyzing what kinds of activities should be attempted to improve the nature of what's happening in that part of the program. Now, with this we have had a quick look at some of the aspects of the different mechanisms that are available to get timing and performance understanding of what's happening when our programs execute. We understood that there are, on all the Unix and Linux systems that we're likely to use, function level profiling using something called Prof is available, and that on many systems that we are going to have access to, basic block level profiling is also available to get information back at a much lower level in terms of the frequency with which, or the number of times that basic blocks, which are 5 or 6 instructions in size on average, were executed when our program ran. And in addition to this, that there are commercially available tools such as Intel's vTune Performance Analyzer, through which we could get information of a much more sophisticated nature, possibly relating to the number of times that cache misses occurred during a particular function execution of relevance to us. So with this we understand that a wide variety of tools are available in connection with profiling and timing, and that they are exactly what are required for us to get better understanding about the way that our program is interacting with the hardware and the operating system, and how therefore pointers to directions that we could take to improve the qualities of these programs. Thank you.